Hello, welcome to another video by Moxie Marine. In this video, I'm installing a crankshaft in an LC9 block. It's from a 2009 GMC truck. It's got active fuel management towers in it, which I'll do another video on that later. I'm disabling active fuel management on this engine. That's the system that converts these engines from an 8 to a 4-cylinder. You do not want that. I'm putting this in a boat, so I definitely don't want that. But anyway, it's an LC9. It's been bored out to a 5.7 bore. So effectively, it's going to be an LS1. LS1s are aluminum blocks. It's going to have an LS1 camshaft, LS1 pistons. So effectively, I'm building an LS1. But the little difference is I'm using 799 heads instead of the 241s. 241s were using LS1s in the early 2000 or 2000 to about 2004. The 799s came out in the LS6 and also used on the LS2 Corvette. So this is going to be basically an LS1 block or engine, and I'm putting the crankshaft in. I'm not going to go into a whole lot of detail about what I've done so far. It does spin free. I turn up my hand pretty easily. We're good to go there. So there's a lot of controversy. What I did want to cover in this video, for a good reason, is there's a lot of controversy about these bolts here. So these are called torque to angle bolts, as opposed to torque to yield. Torque to yield means you can't reuse them. Torque to angle, they can be reused, but you have to torque them a certain way. So torque to angle means that you tighten the bolt up to, say, a minimal torque to 15 foot-pounds just to get them snug. And from there, use a device called a torque angle meter or torque angle gauge. It's this device right here. And so when you use this device, you put it on the bolt. So see if we can put it right here. You put it on the bolt, you hold this, you either put this against something or you hold it steady. You point your pointer at, say, if I want to go, let's say I want it 80 degrees, point it at 200, hold it at 200, then you turn it, and you turn it to that pointer points. It's on 200, I want to go to 280, which would be right there at the edge of my thumb. So this is called a torque angle gauge, and so you turn that to 80 degrees, and it doesn't matter how much torque it takes to do that. So a lot of people don't like this method because it's a little bit more complicated, a little bit harder to do, but there's a reason for it, which I'm about to explain. So the torque to angle method is used because bolts act like a spring. Here's a bolt right here. So this bolt is a certain diameter. There's a diameter here. And so if you calculate the surface or the area of that bolt, the cross-sectional area of this bolt is going to come out to a certain square inches or whatever. And so if you pull on this with a certain pounds and divide it by that square inches, you get the PSI, the pressure it takes that this bolt is pulling down, the pressure, not the pounds, but the pressure. So in engineering science, it's called strength of materials. You have what's called the Young's modulus, and I'm trying to remember what the graph is called, but you have a Young's modulus, which is basically the spring constant of the steel, the spring constant of this bolt. So the material that this bolt's made out of has a certain graph associated with it, and it's basically giving you the springiness of the steel. And that Young's modulus is a factor, a number that gives you, it's a linear relationship between the strain and the stress. Stress is PSI, pressure. Strain is the percent elongation of the bolt. So for example, if this, let's just say this was 2 inches from under the head of this bolt to right here at the top of the threads, that's 2 inches, and you lengthen it by, I don't know, 10%, then that's a 10% strain, all right? So the strain is dependent on the original length, the unstretched length. That's what strain is. It's a percent increase. That percent increase is dependent on the pressure that you use to stretch the bolt. So that's important because the engineers who designed this system, so if you know the pitch of this bolt, which I think I've checked this out to M10 by 2, so 2 millimeters, it means it goes for every full turn of this bolt, the bolt would move down 2 millimeters, okay? So if you measure 80 degrees of turn, that would give you so many millimeters of stretch. And if you divide by the area of this bolt, that would give you the strain, the length of the bolt, that would give you the strain. And then if you have the Young's modulus of the material of this bolt, you can get the stretch and or the pressure. Excuse me, you can get the pressure. So that gives you clamping force. So the reason that engineers want you to turn it a certain number of degrees is because it gives you a consistent clamping force regardless of the torque. If the threads on this thing are dirty or marred up, or the threads in the block are dirty, it takes more torque to turn the same bolt for dirty threads or whatever. So you're not really using that torque to turn the bolt, you're using it to overcome the friction. So by using torque to angle, you always get a consistent clamping force regardless of the torque it takes to turn the bolt. All right, so I was doing some experimenting with this block, and I was trying to channel my inner, I don't know, I'm trying to say the right word, my inner redneck, I guess. No, not redneck, country boy, or whatever you want to call it. I'm a little bit country, you can tell in my voice. So anyway, what I was trying to do is say, okay, there's guys on the internet that say don't use the torque angle method, just use the torque wrench method. And I was saying, okay, I got clean bolts, I oil the bolts, I oil the top, the underside of the head. So I was going to try to see what I was going to turn them. So I know that these bolts here, after the initial torque of 15 foot-pounds, you turn these inside ones an additional 80 degrees, and these outer ones an additional 53 degrees. So what I did was I used my torque angle gauge, and I started with, I think I started with the middle one. Let's see, where's it at? It was right here. So I started with these two. I said, I've read on the internet a lot of guys using 50 foot-pounds to torque these bolts. I felt like I was a little low. So I set my wrench to 50 foot-pounds and turned it to 80 degrees, and the wrench clicked before I got to 80 degrees. That tells me my setting was too low. I cranked it up to 55 foot-pounds and did the next bolt. And again, it clicked before I got to 80 degrees. That says my torque was too low. I then moved on to the next one. So I torqued each bolt in sequence, one at a time, and I narrowed it down to, I got to the point where I got it to 64 foot-pounds. I set my torque wrench on 64 foot-pounds, and that's when it just stopped clicking by the time I got to 80 degrees. So I felt like 64 foot-pounds was the right number, or the torque that I would need. So I finished up torquing the last ones on this end at 64 foot-pounds, and it seemed to work until I got to this bolt. So as I'm tightening this bolt, using my torque wrench set to 64 foot-pounds, and I'm turning it, I was not using the torque angle meter, but I could tell I was going way past 80 degrees. I was well over 90 degrees, even into 120 degrees, and the bolt just felt like it wasn't tightening. So at that point, I am now into what's called the plastic region of a spring. So if you ever pull on a spring too far, so if anybody's ever played with a spring, and you pull on a spring, a tension spring, when you're pulling it, not pushing it, but pulling it, and you let go of it, you'll notice it snaps back to original size, unless you pull it too far. If you pull the spring too far and let go, it will not return to its original size. It will be deformed. It will actually be stretched, and it won't go back to its original size. That's called the plastic region. You have stretched the bolt past its ultimate strength, and you've gone into the plastic region. Now it's stretching, but you're permanently damaging metal, and it's making it weaker, and it will never return to its original length. That's what I've done to this bolt. When I turned it way past 90 degrees, 120 degrees, I could feel it getting weaker and weaker. So this bolt is no good. It's destroyed. This bolt is no good any longer. So I've got to buy a new bolt. I'm going to take a saw and cut it in half so I'll never use it again, because I don't want to find it. So there's a bolt, I can use that. So it's destroyed. So that means I've got one bolt I've got to buy. I'm gonna go ahead and buy an extra one of I'm gonna buy one of these and one of these just to have an extra. I'm gonna buy two of these and one of these to have an extra on hand in case I do any damage. Because the reason I've got to do that, I've got to take this crank back out one more time, and even though it's in good shape, it's turning fine. I've got to take it back out and fix a cam bearing. I've got a number 4 cam bearing. I'm not comfortable with it, even though the cam turns freely. It was tight. I freed it up, but I think the cam bearing has got some, I'm just not happy with it. I'm going to take it out and replace it just because that's, if I don't have a warm and fuzzy about something, I'm going to change it. I don't just leave it. I'll do a video of that later. But anyway, bottom line is that I'm going to have to take this crank back out. And when I do, I'm going to fix the cam bearing. And when I put it all back together, I'm going to be missing a bolt right there. So I'm going to buy a new bolt for that. And I'm buying extra bolts, a couple extra bolts in case I stretch some more of them. But the purpose of this video is discuss torque to angle bolts. I'm getting off track a little bit. But so the point I'm making is that I'm going to use the torque to angle method. I feel like maybe if I hadn't used that method, I wouldn't destroy that bolt. So, and also I did the same with these outer bolts. It turns out that 64 foot-pounds worked to to get these bolts to 53 degrees. The reason being is they're longer, or it could be shorter, I can't remember, but anyway, 53 degrees was able to get this bolt to, or 64 foot-pounds was able to get these bolts to 53 degrees. So these inner bolts you turn to 80, these outer ones you turn to 53, and 64 foot-pounds seem to work for both bolts. The internet seems to say 55 is what I generally read. Well, I felt like 55 was too low, and I think I was right. However, I don't care. I'm going to do it the proper way, the engineered way, which is torque to angle. That's the way I believe everybody should do it. That's what the engineers specified. That's what they want you to do. And all this uproar about using torque to angle, these kids need to get over it and just do the proper thing. Get you the proper gauge, get you one of these torque to angle meters. It's not hard to use, and use it. It's not hard to do at all. And it'll save your engine, or it'll save you from doing the wrong torque. So that's all I want to say in this video. Again, I'm fixing to take the crankshaft back out and fix the cam bearing, but you should use torque to angle and not torque when you're setting LS1 main caps. The head bolts are torque to yield. That means once you've torqued them one time, you're not supposed to reuse them, because I believe a torque to yield bolt, could be wrong about this, I'll do a little more research, but a torque to yield does put that bolt into the plastic range, which means it's stretched permanently, and they do that for a reason. They want to get a consistent clamping force every time you tighten that bolt, or when you use those kind of bolts, or they want to get a consistent clamping force when you use those bolts. And therefore they go into the plastic range, and that means it's always clamping with a certain, because in the plastic range, the more you tighten, you're not creating any more stress. You're just keeping the same clamping force regardless how much more you turn it. So you definitely don't want to turn those past the angle that they specify on a torque to yield. So for all the internet engine builders out there, use the angle method. If the engineer calls for it, if the engine builder, engine designer calls for it, use the torque to angle or torque to yield method. That's the way you should do it. And stop all this crap on the internet about switching over to a torque wrench, just because that's the way you used to do it back in the 50s and 60s. Things have changed. These are modern engineered engines, and that's what you should do. Use the torque to angle method. All right, I think I've said enough about that. I'm gonna go ahead and get this crank back out and work on the cam bearing. Thanks for watching.